In the 4th century BCE, the Dionysian festivals drew crowds of up to 15,000 citizens to monumental amphitheaters carved into the Mediterranean hillsides. To reach the furthest rows, a single unamplified voice had to travel more than 50 meters through open air without the aid of modern electronics. Physical laws dictate that sound intensity drops radically as it expands across a distance. In an open-air environment, these waves also face the constant interference of Mediterranean winds and the collective murmur of a massive audience. Despite these obstacles, spectators in the highest tiers could hear complex poetic dialogue with startling clarity. This suggests a mastery of sound propagation that defies modern intuition about distance and volume. Understanding how these performances functioned requires looking past the art of drama to the architectural and biological principles that made such a broadcast possible. Historical inquiries often begin with the iconic theater mask. These oversized accessories allowed a small number of male actors to portray a vast range of characters, from gods to mythological heroes. Because of the mask's rigid, funnel-like mouth opening, many theorists assumed it functioned as a wearable megaphone, designed to mechanically amplify the voice toward the audience. Modern researchers tested this theory by placing exact physical replicas of masks on head and torso simulators inside anechoic chambers, specialized rooms designed to eliminate all external echoes. Acoustic measurements showed that the masks provided a modest 5 decibel boost, but only to low frequencies below 1000 Hz. This range carries raw vocal power and vowel sounds, but does nothing to clarify the high-frequency consonants essential for intelligible speech. The rigid shell completely enclosed the actor's head and neck, trapping acoustic energy. Bouncing sound directly back into the ears, the internal volume often exceeded 110 decibels, the equivalent of operating a chainsaw next to the head. While the masks equalized the tone and improved side projection, they functioned as an auditory burden for the actor. The primary work of acoustic projection was actually accomplished by the stone environment. The focus shifts from wearable accessories to the monumental stone structures, specifically the relationship between the performance floor and the stage building behind it. As this diagram shows, the stone skein acted as a highly efficient acoustic reflector. Radiating backward from the performer, sound struck the hard stone and bounced toward the audience, reaching listeners just milliseconds after the direct voice. This proximity exploited the Haas effect, a neurological phenomenon where the human brain fuses two identical sounds arriving within 40 milliseconds of each other. Instead of hearing a muddy echo, the listener perceives a single, louder, and fuller sound. By ensuring these early reflections arrived within this critical biological window, the Greeks used geometry to naturally amplify speech without sacrificing its clarity. At the theater of Epidaurus, the audience seating provides another layer of engineering. The limestone rows are not smooth. They feature a continuous corrugated surface formed by the staggered edges of each step. 3D wave-based computer modeling has demonstrated that this specific corrugated geometry allows the seating to function as an advanced acoustic filter. This diagram illustrates acoustic diffraction. The ridged stone scatters low-frequency background noise below 500 Hz, while backscattering high-frequency consonants toward the audience. However, removing sounds below 500 Hz also strips the voice's resonant fundamental tones, which should sound unnatural. The human auditory cortex compensates for this loss through a pattern recognition process called virtual pitch. When the ear receives high-frequency harmonics, the brain analyzes their mathematical relationship and fills in the missing fundamental tone, reconstructing the perceived warmth of the voice. The theater architecture acts as an equalizer that suppresses environmental interference, allowing the listener's brain to reconstruct a clear auditory signal from the surviving frequencies. Ancient architects optimized signal-to-noise ratios through structural design, mastering the relationship between geometry and sound long before the mathematics of wave dynamics were formalized. These principles of early reflection and strategic geometric filtering remain the foundation of modern architectural acoustics and venue design. In the 19th century, engineers began translating these intuitive spatial relationships into formal equations, allowing for the design of refined indoor environments like Boston's Symphony Hall. Today, contemporary projects like the mass timber structures in Vancouver continue to utilize the semicircular open-air layout to cradle the audience and optimize sound distribution. Ancient Greece demonstrated that commanding the attention of thousands is possible through a mastery of physics and human perception, creating an architectural legacy that remains audible 2,000 years later.